video, we're going to be working with stoichiometry. And in stoichiometry, what you're doing is you're taking measurements of one either reactant or product, and you're converting into units of another reactant or product. So for example here, I give you A, it can be a reactant or a product, and you're going to convert into B. Now, this isn't a new concept because what we looked at in the last video was going from either mass, volume, or particles into moles. The only new thing here is going from moles of A into moles of B. So to go from terms of A into terms of B, you need to get into moles and then use your mole to mole ratio. Now your mole to mole ratio you get from the actual reaction. Okay? So let's look at how we do that with an example problem. Now, before we go ahead, remember going from mass of A to moles of A, you use your molar mass. Going from the volume of A to moles of A, you use 22.4, assuming that you are at standard temperature and pressure. And then from particles to moles, remember you use Avogadro's number. Okay, so let's look at an example. Here it says, given the formula, okay, so nitrogen reacts with hydrogen to produce ammonia. How many grams of ammonia will be produced if 67.2 liters of nitrogen reacts with excess hydrogen at standard temperature and pressure? So our given here is 67.2 liters of nitrogen gas. So what I'm going to do is I'm going to first get into moles of nitrogen gas, because then I can get into moles of ammonia. So I'm going to put liters of nitrogen gas on bottom. I'm going to put 1 mole of nitrogen gas up top. Okay. I know I'm at standard temperature and pressure, so I'm just going to plug in 22.4 here. Now to go from moles of nitrogen gas into moles of ammonia, I'm going to put moles of nitrogen gas on bottom, and I'm going to put moles of ammonia up top. Okay. So this is the only new concept that we're covering. This is review from the last video. So what I do for the mole to mole ratio is I simply use the coefficients that are given to me in my balanced reaction. So the coefficient for NH3 for ammonia is 2. So for every 2 moles of ammonia, you're going to have, well, there isn't a coefficient here, so that's going to be 1 mole of nitrogen gas. So now I'm in moles of ammonia. So I don't want to be in moles of ammonia, I want to be in grams. And so I'm going to go from moles of ammonia, so for every 1 mole of ammonia, and then I'm going to put grams up top. Now to go from moles of ammonia into grams of ammonia, I need to use the molar mass. And so the molar mass of ammonia, nitrogen is 14.02, hydrogen is 1.008, but there are 3 hydrogens. And so when I calculate that, I get for my molar mass 17.034 grams per mole. And so what I'm going to do is I'm going to take 67.2, divide it by 22.4, multiply it by 2, and then multiply it by 17.034. I want 3 significant figures, so my final answer is going to be 102 grams. And that's my final answer.
So in this video, I'm going to be talking about limiting reactants. Now, a limiting reactant is the reactant that actually limits the amount of product that can be formed. So for example, if I have plenty of chocolate and marshmallows to make s'mores, but I only have, let's say for example, enough graham crackers to make 2 s'mores, the graham crackers are going to be my limiting reactant, because without graham crackers, even if I have tons of marshmallow and chocolate, I'm not going to have enough graham crackers to make my s'mores, and so my graham crackers would be my limiting reactant. The excess reactant is the reactant that is not completely used up. So for example, in that analogy, the marshmallows and the chocolate would be your excess reactant.
So in this limiting reactant problem, I'm given 2 different quantities of my reactant, 1.5 moles of aluminum and 3 moles of chlorine. And I'm asked how many grams of my product, aluminum chloride, are going to be formed. And so what I'm going to do is I'm going to figure out how many grams of aluminum chloride can 1.5 moles of aluminum produce, and how many grams of aluminum chloride can 3 moles of chlorine produce. And whichever one produces the least amount, that's how many grams of aluminum chloride will actually be able to be produced. And whichever one produces that amount, that is your limiting reactant. So the first thing I've got to do though is I've got to balance. Well, I've got 3 chlorines here and 2 here, so I'm going to put a 3 coefficient in front of here, a 2 here, and then I'm going to put a 2 here. So now I can actually convert into grams of aluminum chloride. So I'm going to start off with 1.5 moles of aluminum, and I'm going to get into moles of aluminum chloride because I don't need to convert from grams or anything. I'm already in moles of aluminum. So I'm going to put moles of aluminum on bottom, and I'm going to put moles of aluminum chloride up top. And then from moles of aluminum chloride, I can go directly into grams of aluminum chloride. So grams of aluminum chloride up top, and then I'm going to put moles of aluminum chloride on bottom. Now, to go from moles of aluminum to moles of aluminum chloride, I need to put the mole-to-mole ratio. Well, the coefficient for aluminum chloride is 2, so for every 2 moles of aluminum chloride, I have 2 moles of aluminum. And then here, for grams to moles, I need to put the molar mass of aluminum. So I put a 1 for moles of aluminum chloride, and then I put 133.33 for the molar mass of aluminum chloride because I calculated that. Well, when I get my answer, I actually only want 2 significant figures. And so what I'm going to do, because 200 is only 1 sig fig, I need to convert 199.995 to have 2 sig figs. Well, 200 doesn't work, obviously, so I'm going to convert this to scientific notation. So it's going to be 2.0 times 10 to the second grams. Now I'm going to do the exact same thing, but I'm going to do it for chlorine now. So I have 3 moles of chlorine, and I'm going to convert that into first moles of aluminum chloride and get rid of moles of chlorine on bottom. And then I'm going to get into grams of aluminum chloride. Moles of aluminum chloride on bottom. Okay, so here again, this is just going to be 133.33 for every 1 mole, but here I'm going to use the mole-to-mole ratio. For every 2 moles of aluminum chloride, I have 3 moles of chlorine. And so when I do this, what I get, I end up needing to round just to 1 sig fig, so I end up getting 300 grams of aluminum chloride. So I've got 2 different amounts of product. I've got 200 grams and 300 grams. So this is the amount that's going to be produced. And the reason why is after I've made 200 grams of aluminum chloride, I am now out of aluminum. I have no more. So even though I could make more with chlorine, I could make 300 grams, there isn't enough aluminum to make 300 grams of aluminum chloride. And so my limiting reactant is going to be aluminum.
The next thing I'm going to talk about is theoretical yields. Now, your theoretical yields is the quantity of product that you calculate to form when all of the limiting reactant is consumed. So when we're doing our calculations, that's the amount of product that we anticipate should be formed. However, the actual yield is the amount of product that actually is obtained in the lab. Now, your actual yield, it tends to be less than your theoretical yield, and therefore we have what's called your percent yield, which is measuring how well you did in obtaining your product. So to find your percent yield, you take your actual yield, you divide it by your theoretical yield, and you multiply by 100%.
So in this problem, it gives me my reaction, and it tells me that my limiting reactant is iron 3 oxide. So I don't need to determine how much of my product is going to be formed because I automatically know that 150 grams is what's going to produce my product. And so I'm going to take my 150 grams and I'm going to figure out how many grams of iron that theoretically should make. If I give you 2 different amounts of reactants, then you would have to do a limiting reactant problem, but here I don't need to because I tell you it is the limiting reactant. So what I'm going to do is I'm going to go from grams of iron 3 oxide and I'm going to get into moles of iron 3 oxide so that I can then get into moles of iron. And then finally, I can get into grams of iron. Okay? So what I need to do is here I need to plug in the molar mass of iron 3 oxide. So for every 1 mole of iron 3 oxide, there's going to be 159.7 grams. Because remember, you take the molar mass of iron, multiply by 2, and add to that the molar mass of oxygen times 3. Here I'm going to use my mole-to-mole ratio. So there's 2 moles of iron for every 1 mole of iron oxide. And then here I need to put simply the molar mass of iron. So it's 55.85 grams of iron for every 1 mole of iron. And so what I calculate here, because I want 3 significant figures, I calculate that I'm going to produce 105 grams of iron. So this is my theoretical yield. Now to calculate my percent yield, I'm going to take my actual yield, what I actually got in the lab, which would have to be given to you, and is given to you right here. I tell you you produce 87.9 grams of iron, and you're going to divide that by your theoretical yield, and then you're going to multiply that by 100%. Okay? This value should never be above 100 because that doesn't make sense. Yes, reactions aren't completely efficient, so you're not going to end up with an actual that is equal to theoretical, but actual should not be above your theoretical. So you're going to take 87.9 grams, and you're going to divide that by what you theoretically should have gotten, which is 105, and then you're going to multiply that by 100%. And so what I end up getting for my percent yield in this problem, since I want 3 sig figs, is 83.7%.